of the final day of the QSim Conference. I just want to start with a reminder that you should have received a link to a survey for the conference, which will help us to collect some information about how things have gone. It would be great to get your feedback, so please take just a couple of minutes to fill that out. We'll really appreciate it. And let's get started with this session. So it's a pleasure to introduce Michael Gullans, who will tell us about architectures and algorithms for early fault-tolerant quantum computers.
Great. OK. Thank you, Andrew. Thanks for having me here. Happy to present at QSim. So let me just get started. And I'll start off with some general motivation for this talk. And then I actually want to dive into two kind of recent research directions we have, which I think are very relevant to the specifically QSim. So I'll tell you about that in most of the talk. OK, so I think we've heard about this a lot at this conference and throughout the last few years that recently we're entering this era of fault-tolerant quantum computation where people are starting to put together physical qubits into logical qubits, and we're beginning to think about quantum algorithms in this sort of new kind of computational model where you're manipulating logical degrees of freedom. So there's results shown here spanning industry and academia. So on the left is the academic work, and then on the right there's the huge push from industry, which is really driving a lot of this field. So just to organize the kind of status of where things are, so we like to, recently the way we like to organize this is in terms of thinking about quantum operations, the number of coherent quantum operations you can do before you have noise that destroys your system. And so currently we're still in this sort of kiloquantum op regime, which is sort of NISQ and early fault tolerance. And there's not a lot that as we all know, there's not a lot you can do in this setting. So a lot of the work is about exploring algorithms and error correction more at a fundamental level. And then there's one kind of direction for advantage, which is this random circuit sampling, which is actually quite a nice and rich problem, but it doesn't have this kind of practical usefulness. So as we look to the future, so in this what we could call mega QOP and beyond, you start to get into settings where you can really think about more practical advantage, specifically in the context of quantum simulation. OK, so I wanted to just show you this a kind of cartoon roadmap that we put together. This was for a NSF strategic plan for neutral atom quantum computation. But I think it sort of applies generally for how people are thinking about the sort of trajectory of these devices. So in terms of applications, as I mentioned at this stage in the present day, we're still at the level of sort of testing and trying to understand quantum advantage. But there's optimism in the field that as we push to these sort of larger mega QOP machines, there will be potential for particularly quantum simulation applications. And then further on, looking at things like Shor's algorithm and optimization problems of that nature. So on the other side, there's as this applications develop, there has to be this transition to logical qubits, and there's still currently a plethora of strategies. So I think a lot of the community is still exploring, what's the best way to think about this. In that sense, this era of early fault tolerance is actually a very exciting scientific frontier, just in sort of really testing these theoretical ideas out in physical systems. So kind of the hope of people like myself and I think many others is that so when we give these kind of roadmaps, they tend to be for accepted sort of strategies based on, say, the surface code with magic state factories. But the hope is that with sort of co-design and optimization, we can actually push these even closer to present day. And so that's sort of the spirit of my work and also the directions I'll tell you about in the talk. So with that, let me transition to the technical part of the talk. So I'm going to tell you about two kind of recent research directions in our group, which are very much exploratory, but I think they're kind of exciting for this kind of QSim conference. So one direction is about fermion-qubit fault-tolerant quantum computing. So this is actually building on a lot of the progress in neutral atom quantum computation to try and imagine an architecture where you have the constituent degrees of freedom are sort of fermionic qubits. And I think I actually had to leave the conference for Wednesday and Thursday. I think we heard a talk about this from the Innsbruck group earlier in the week. So this is sort of related to that work as well. The other project I want to tell you about is a kind of interesting direction where we're sort of using ideas from statistical mechanics to show that there's actually a sort of new, we find a new phase in the context of CSS codes or the surface code, where it looks like you can do a fault-tolerant transversal gate with kind of continuous parameters. So that's kind of a maybe controversial statement, but I'll explain that in the second part. So this first project, these are my collaborators on this. So Alex, Shukart, and Ella are former postdocs at Maryland. And then the second project is my student Eric at University of Maryland, who's been leading this. And we've also been doing some experiments through this QLab partnership at Maryland, which has a partnership with IonQ. OK, so let me jump into the first part of the story about fermions. So as we know, the fermions are important they're really crucial for quantum simulation and thinking about these kind of more practical applications for materials and even high energy physics, nuclear physics. We also know that there's a lot of work on classical computational methods, which has taught us that these are hard numerical problems. So we have a range of different methods that work in different regimes, and you kind of, depending on what problem you're working on, you sort of choose the appropriate method. In the context of quantum devices and quantum simulation, there's been really, over the last decades, there's been really amazing progress on this sort of, we'd say, sparse connected models. And even going to large system size in the case of analog systems. But there's still a lot of room for improvement. And just to flash some of the recent work in this area, so this is showing some experimental results on fermion time evolution in quantum systems. In both of these cases, you can think of this as simulating something like the Fermi-Hubbard model. So on the left, the current system sizes are limited to around handfuls, tens of particles, so quite limited simulations, and also still local models in some sense. In the analog case, you can go to much bigger systems, but then you have less control over the Hamiltonian. So in the case of applications like chemistry and material science, we know that the Hubbard model is not sufficient. These tend to be they have much longer range or much denser interactions in the problem that don't easily map into this kind of paradigm. So the thinking, and this is the jumping off point for this work, is that we want a sort of universal and high precision fermionic quantum computer. So we have analog simulators based on native fermions. But we'd like to start thinking about digital systems in that way, and particularly want to think about the future where we have error correction as well. So the sort of architecture we're going to consider is this fermionic quantum computer, where we have so we imagine we have atoms trapped in an optical lattice or tweezers, and the distinction from the Rydberg systems we've heard about is that these would be actually a fermionic atom. So you would have two kinds of encoding. So you have either the presence of an atom or not is one degree of freedom. And in addition, you also have like qubits, which are just internal spin states of the atoms. So this is the more conventional encoding for these problems. And I should also mention we have a sort of parallel direction. So this, what I'll focus on is the AMO type systems. We have a parallel direction on solid state qubits where you also have native fermions. And that's a collaboration with Sora Davudi, as well as others. And yeah, you can read about that more in this paper. And this is thinking about simulating high energy physics. Okay, so so let me build up the ingredients we need for our problem. We want a digital fermionic quantum computer. So we need a phase gate. That's actually, so e to the I theta in hat, where in is like the number operator. That's easy to implement just with a laser. So that's just a local energy shift. There's a hopping gate. That's also easy to imagine just by modulating the tunneling barrier. And there's a interaction gate, which we envision using, again, these Rydberg states to do density-density interactions of the fermions. So if you just have number conserving operations, this is already a universal gate set. So one other aspect we consider is that we also can imagine having qubits in the same platform. So you can have a qubit fermion gate, which again is just another density-density type interaction, but where one of the operators is now a qubit operator. And this becomes universal for qubit fermion computation. There's one other possibility with fermions. So fermions, they have the parity conservation, but that still allows something called a pairing interaction, which gives rise to superconductivity. And that, instead of having p and p dagger appear in pairs, that has sort of p squared or p dagger squared. And currently, there's not direct implementations of these kind of pairing gates, except maybe in the context of superconductors or something like that. But definitely not in this kind of digital setting. But this would be what's needed for the whole fermionic gate set. So the other aspect we want to consider is errors in fermions. So there's two types of errors you can have. You have phase errors, so this density operator, but you can also have things like atom loss, which is linear in P. It's helpful to actually, just mathematically, it's helpful to map, these are complex fermions. It's helpful to map them to Majorana fermions through this approach. And then these are the types of errors you have are gamma. These are sort of like the real and imaginary parts of the operator. So gamma and gamma tilde, and then that's sort of like an x and y error, and then you have a z error, which is the product. Okay, so so we have a universal gate set, and we also have noise, and so we want to think about how we can protect against that using error correction. And so now, and the sort of the idea we want to explore is whether you can take sort of mini physical fermions and actually encode a logical fermion. And what I mean by that is that what's special about fermions is that when you exchange them, you get this minus sign in the wave function. So that leads to that's sort of the origin of the overhead. And when we were trying to do quantum simulation with fermions, trying to encode these anti-commutation relations. But if you have physical fermions, it sort of is just part of their behavior. And so what we want to do is take physical fermions, redundantly encode them into a logical fermion, and then when we start exchanging fermions in between the two blocks, you'll pick up a minus sign every time you exchange a pair. So if you exchange 2, you get a plus sign, and then if you exchange an odd number, you'll get the minus sign back. So in order to have this property that you have a logical fermionic operator, what that means is that because every time you exchange a code block, you want to get this minus sign, it means that you need logical fermionic operators to be odd weight products of the physical fermions. So that turns out to be a simple condition to state, but actually hard to satisfy in practice, as I'll explain. OK, so let me give you some examples of fermionic codes. This is an example that doesn't work. So one idea is you could just take the surface code and turn it into a Majorana code. So you might imagine using the mapping from the qubit to the Majorana operators. So the Z-type checks would become a product of gamma tilde, and the X-type checks would be the product of the gammas. The problem is that in the case of the surface code, you have checks of the same type overlap on single sites occasionally. So like site 2 and site 5, for example. And then because of the anti-commutation, you'll actually break you won't have a commuting set of operators. So you can't really think of it as a stabilizer type code. So this actually doesn't work. So you have to be a little bit more careful when you're trying to design fermion codes. You have to account for these special commutation relations. But it turns out there's a nice and simple example. So there's the surface code. Another classic error correcting code is called the Steen code. It's the 713 code for qubits. That's parameters. And so in this case, it has this property that all its X checks actually are also, the Z checks have the same structure. So when you replace, when you do this mapping where you replace the product of X's by products of gammas, you end up with a valid Majorana code now. And this is nice because the gammas are sort of sitting on top of each other. You can actually think of this as 7 physical fermions. So you sort of virtually, you take the physical fermion, you split it into 2 Majoranas to make this code, but then they actually sit co-located in space. So it's really just 7 fermion sites. And these kinds of code constructions for Majorana codes in a sort of different context were sort of explored in some of these early papers here by Bravi and Terhall. OK, so as I mentioned, so far in all these fermionic platforms, like neutral atoms, the non-number conserving gates haven't been realized. But it turns out that's crucial for quantum error correction with fermions. And so in particular, there's a sort of simple no-go theorem we can prove, which says that if you just have number conserving operations, it's not sufficient to encode logical fermions. And so let me just go through the proof briefly. So the idea is to use 2 kind of conditions. So one is something called the nil-Laflamme conditions. So for an error to be detectable by a code, so P is the projector onto the code space, when you act on the error on both sides, it has to sort of go back to the code space in a way that doesn't depend on the error that was applied. And it just has to go back to it's proportional to the projector. And then so it doesn't distinguish the states within the code space. And then the other condition we need is the logical fermion. So the logical fermionic operators have to anti-commute with each other. OK, so here's the sort of the no-go theorem. So let's imagine that we only have number conserving operations and our code eigenstates are number eigenstates. So that means the logical 0 and 1 are eigenstates of the number operator, which is just a sum of single site densities. And now this means that it commutes with the code space projector. So we have this equation. So using the nil-Laflamme conditions, we can also, when we do P on the left, then it will, because this is just a single site operator, if our code has distance 2, which means it corrects one phase error, then it would, we also have the condition that n times p is proportional to p itself, and that means that all of the code, the logical states have the same number eigenstate. And so n0 is n1. And now what this means is that the logical operators, because they all live in the same number space, logical operators can't change fermion number, which means they have to be quadratic in P and P dagger. And this means that whenever you have two logical code blocks, the logical fermion operators will be quadratic, so they'll commute with each other. So you won't have logical fermions. OK, so in order to do, I mean, on the other hand, we know just from these theoretical arguments that fermionic codes exist. So to make them physical, we have to be able to implement this pairing interaction. So our proposal is to have some direct pairing gate in the system. And this has actually been explored in the past in the AMO community. And so one way to imagine this is that you take a Feshbach, you take a molecule, like a set of paired fermions, and then you can actually break it apart into two unpaired fermions. And that effectively acts as that will, from seemingly nothing, from this bosonic degree of freedom, it will create fermions. So it acts like a pairing term. So you can think of it in terms of the Hamiltonian. You can sort of write down a simple model, which is like B for the molecule, and then it creates a pair of fermions. And the idea is that if this bosonic system is in a coherent state, then similar to a laser, we can replace B by its expectation value, and you directly realize this kind of pairing gate. So the proposal is that you make a kind of BC of these Feshbach molecules, either in a tweezer or in a lattice system or in some kind of trapped geometry. And then you have a way of dissociating them into these pairs of fermions using RF fields. And what you can really, this is, if you're not used to thinking about fermions, this can be counterintuitive. But it's actually the same physics that goes into how lasers work, even the presence of energy conservation. And you can directly compute the gate fidelity. And what you see is that as you increase the sort of size of this BC, the gate fidelity improves. OK, so right. So now now that we have the ingredients we need for these error-correcting codes, and as I gave this particular example of the color code, that actually has certain transversal gates which we can use for computation. So conventionally we would say it has a Hadamard and C0 gate, but these gates actually don't exist for fermions, so you have to make some adjustments. But you can show that for the same code, these are kind of like the analog of Clifford gates for fermions. You can replace them by these allowed gates, and then these emit transversal operations. And to get universality, we need something like this additional T gate. So the other ingredient we need is that I mentioned is we want to. It's actually it's convenient to think about qubits and fermions together. So we want a way to entangle logical qubits with logical fermions. So that can also be done transversally. So if you imagine you have one of your code blocks is in the same Steen code, but for qubits, then you can do a transversal gate with the fermions through this interaction. And this is a cartoon that we sort of made up, from real data. So we imagine you have a logical qubit on the left and a logical fermions on the right, and then you can just pick them up and implement the gate. So that's kind of the proposal. Let's see. Okay, so the last piece we need is the T-gate. So that can also be, that can actually be, because we have this coupling to qubits, we can borrow the T-gate from qubits. So if we have a way of doing logical T-gates on qubits, then we can also do it on the fermions through this kind of circuit. Okay, so right, in terms of the architecture, I've sort of, in this context of these neutral atom systems, I've sort of put all the pieces together. We have logical fermions, logical gates, error-correcting codes, and also I've shown you how at least one way to implement these physical gates. And now the sort of important question, which is where we put a lot of focus, is trying to understand whether this has there's any advantage to going from qubit quantum computers to fermionic quantum computers, or what potential advantages there could be. So what we want to think about first is quantum simulation of this kind of chemistry Hamiltonian, which you can write down more sort of conceptually in terms of kinetic energy. There's Coulomb interactions with ions and electrons, and then electron-electron interactions. This is the sort of first quantized version of it. So then, of course, this has been studied, for many years now, and these algorithms for doing, say, time evolution of this Hamiltonian have been highly optimized. And so we have estimates for, on the case of qubits, we have pretty good estimates for each of them, at least upper bounds. So for the electron-ion interaction, because if we just think of the ions as frozen in space in the sort of Born-Oppenheimer approximation, then that's just single-site gates, so that can be done in constant depth. Some of the kinetic energy term is more complicated. So the current time for time evolution scales with linearly with n, and similarly for the electron-electron interaction. So one of the first results we have is, and this is maybe the one place where the fermionic sort of character enters directly, is that we can, if we're doing a material science simulation, then it's convenient to work in what's called the plane wave basis, and then by doing what's called a fermionic fast Fourier transform, you can actually implement the kinetic energy in depth 1 up to the cost of this fast Fourier transform. And for fermions, the fast Fourier transform is essentially just a routing protocol with some single qubit gates. And that can be done in log depth, assuming you have long-range interactions. Whereas for qubits, it's not currently known how to do it in log depth. So the current implementations would be linear depth. Okay, so we have a speed up in the kinetic energy potentially, or at least a much lower upper bound in the case of the kinetic energy. And then the remaining piece so ideally we'd want to improve the entire algorithm to be log depth. So for that, you need to speed up the electron-electron interaction. I think in the interest of time, I won't go carefully through that, but we actually have two ways of doing it. So one they use essentially different numbers of ancilla. So one approach can implement it in constant depth, but it needs n squared ancilla. So the other approach we have is a more sophisticated algorithm that requires doing quantum arithmetic in the fermion basis. Essentially, you're doing a Fourier transform of the density operator themselves. So that lets you use much fewer ancilla, only log ancilla, And this, right, and this idea has also been explored in some work by Lowe and Wiebe. But the nice thing about this is that with this method, you can do the electron-electron interactions in log squared depth. Yeah, so the details are in our paper, so I won't go through them. Right. So yeah. So in the case of the fermions, we have a full solution, which is polylog n for this quantum chemistry problem, and whereas currently the qubit algorithms are linear depth. So that's kind of the main result, and that's part of the motivation. I should say that we're also working now that we have these upper bounds from fermions, we're working on improving reducing the upper bounds for qubits, and it's potential that potentially we can get the same result for qubits as well. Okay, so now in the last 5 minutes, let me kind of quickly go through this result on continuous transversal gates, which could be helpful for speeding up quantum simulation, like say if you're doing trotterization or something like that. So the sort of high-level summary is that we have a new approximate protocol for doing a continuous angle z rotation in the surface code that uses transversal z rotations plus decoding, and its runtime is logarithmic in the sort of precision. In practice, you only need a couple rounds, it turns out. So I'll explain that in a bit. But the idea is that what we're doing is we have a way of doing essentially random logical z rotations with small angles, and by piecing them, sort of directing this process through feed forward, we can arrive at a particular target angle. So the kind of ingredients we need for our protocols, you need a error-correcting code, you need the ability to apply physical continuous z rotations, you need a decoder that can handle this situation, and you also need fast classical simulation. So this is the one sort of round of the protocols. You apply transversal z rotation, you measure the syndrome, and then for a large class of CSS codes, you can prove that after the syndrome measurement, what it does to the logical qubits is it implements a logical z rotation, but with a random outcome. And so the way you can think about this is the input is the physical angle you rotated, the output is this random syndrome, and then you have to compute, like decode this logical angle. So that's kind of our black box. In terms of computing this angle, this is actually a bit for the specific cases of the surface code. It's like this rotated surface code family. This has been worked out through a mapping to free fermions in this nice paper by Bravi and company. And then what this parameter, this input parameter does is it lets you, the rotation you apply, it lets you tune the variance of this angle. So you can go from a very narrow distribution to a very wide one at large angle. And it turns out to get, at least theoretically, if you want to achieve, if you want to sort of pick the optimal variance, what you do is you choose it so that the variance of this distribution is close to the target. It's sort of equal to the distance to the target angle that you have, and you can show that will converge exponentially. And so this is a comparison of the sort of t count versus the sort of stopping time of our algorithm for different gates. And you can see this kind of log scaling that you also get for Clifford plus T synthesis. Okay, so in the last minute, I want to talk about the fault tolerance of this protocol. So far, there was no noise. So it turns out that noise in the measurements and also X noise during the protocol doesn't affect its noise robustness. Where the subtlety comes is when you have Z noise right before the first measurement. And so now I'll explain how you don't have a sort of exact fault tolerance against this type of noise, but I'll show you a sense in which you have approximate robustness. OK, so now what I want to go through is actually, so it suffices, because we don't have to worry about measurement errors, because we're just, say, if you did repeated rounds, it suffices to just consider the channel coding problem. So you just have a layer of surface code followed by a perfect Z measurement. But the noise that is applied is this mixture of incoherent and coherent noise. And we parameterize the strength of the coherent noise by this relative dephasing parameter. So there's other ways to characterize it, but I won't go through that. So if you think about the logical noise channel that gets applied, so what you'll see is this, with both these parameters, you see this kind of phase diagram shown here, where there's this kind of region at low noise rates where the logical rotation is converging to 0. So in quantum error correction, there's 2 points on this. So these two extreme axes are very well understood. But what goes on when both types of noise are present is only recently been considered in the community. In this case, there's no efficient algorithm, so it's more difficult to study. OK, so the question I want to explore is what's going on in this sort of mixed regime below threshold. And so what we want to study is this. You have you sort of have this unital noise channel followed by a syndrome measurement, and we want to understand what's the syndrome condition noise channel. So we use a tensor network algorithm to compute this, and that can be done, approximately at least. And we're using this method from Dharmawan. And this is what we see. So what's interesting is that there's actually two phases we find. So if you go to weak incoherent rate and then increase your coherent rotation angle, you see this regime where the sort of relative dephasing condition on the syndrome converges to 0. And we can actually understand this behavior using sort of statistical mechanics mappings, which I won't go through. So I'll just end with the kind of highlight for the quantum simulation context, which is that, so we see two things. So one is that as you increase the code distance, the logical angle that you do decays exponentially. But it turns out that the relative error you make in that logical angle also decays exponentially. And it implies that even if you're doing an order 1 rotation, so you're repeating this for many rounds, you'll make an exponentially small error in the rotation. And so this protocol, assuming it can work in a realistic circuit level noise context, would circumvent the need for any ancilla or post-selection in doing at least small angle logical gates. And so with that, I'm running out of time. So let me just finish my slide with the sort of summary and outlook. So in the context of this, so I told you about these two results. So this architecture for fermion-qubit fault-tolerant quantum computing. I think there's a huge amount of open questions for this, in particular when it comes to implementations and the effect of interactions. There's also a question whether you can get algorithmic speedups for non-simulation tasks. And then, as I mentioned, we're thinking about trying to reduce qubits so that they're on par with the fermions. In the case of this continuous transversal gates, we've been doing experimental tests in this QLab partnership, so that's work in progress. We have another set of results in collaboration with Matteo Ippoliti showing how you can use this to make logical K designs. And yeah, there's a lot of open questions about actual performance in practice. So yeah, thanks for your attention.
Okay, thanks, Michael. We have time for maybe